left off more or less. So just to remind you of what we're doing, well, I've written this sentence about 85 times now. No doubt one or two of you are keeping count. Let G be a group, and we're going to take an element A in G, and then what cyclic groups are all about is taking powers of a particular element, and that's called the cyclic. Putting all those powers in a big bag gives you what's called the cyclic subgroup generated by A. So this is just reviewing what we did last time. I'm using some words in and among that we introduced last time as well. So we use this pointed bracket notation, pointed brackets A. So I'll write this down in two ways. First, using slightly sloppy notation, which is acceptable but slightly sloppy. I think I mentioned this in at least one of the tutorials yesterday. And then I'll write it down in more precise notation. So the kind of crudest way to write this down is we just take all powers of A, where n here could be any integer, negative, 0 or positive. We take all powers of A. We can compute powers because powers are just iterated multiplications, and we can do multiplication because we've got a binary operation on the group G. So we can take powers of A, and we take all possible powers and put them in a bag. And that's what we mean by pointed brackets A. A slightly more sophisticated way of writing this, in fact the correct way of writing this, we should really write this as something like this. The set of all group elements X such that X is a power of A. So in other words, there exists some integer n for which X is that power of A. So the first version of this is sloppy but acceptable, and the second one is more precise. I'll let you think about why the first one is slightly sloppy, but I'm quite happy if you use the first description. I'll use both in and among. The second one is a bit more precise. So that's what pointed brackets A means. It's a set of all powers of A. And what we showed last time is that pointed brackets A is a subgroup of G. So by definition it's certainly a subset, but it's actually a subgroup. And in fact, it's the smallest subgroup of G that contains A. And we proved that last time. So at the very least, this construction gives us a way of constructing subgroups of any group. We just take a group, we choose an element in the group, and immediately we've got a subgroup of the group. And since subgroups are going to be used to kind of probe the internal structure of groups, this should be useful because we can generate subgroups. Okay, so that at first sight, that's a use of cyclic groups. So we had one or two examples last time. Let's do one or two more examples. Well, let's look at a very important group. Let's take the integers under addition. So that's a very important group. Here I've written the binary structure in full with a set and a binary operation. Often we just write Z with the understanding that if we're doing group theory, Z is equipped with its addition. So this is a bit more precise than that, but saying the group Z, everybody knows if you're doing group theory that you mean the integer Z with the binary operation of addition. So the claim is that Z, and I'm reverting to the sloppy notation now, is a cyclic group. And as I explained last time, when I say a cyclic group, I mean that there exists an element for which the subgroup generated by that element is the whole thing. Okay, so let me just say that there exists an integer a such that if I look at the subgroup generated by a, I actually get the whole thing. How do I generate the integers from one element? We've got to be slightly careful here because we're using additive notation. And this is a possible source of confusion. In general, when we're talking about groups, we tend to use multiplicative notation, okay? But if the group is something like the integers where the binary operation's addition, we're not going to suddenly start using multiplicative notation because that would be very, very, very confusing. So we're using additive notation, so we've got to be careful about what powers mean. And I'll just make this remark once and for all. So if we've got a and z, say, whereas before, for instance, if I was computing a squared, I would be using multiplicative notation. So a squared means a times a. We're now using additive notation. So the thing I'm talking about is a plus a. And we're not going to write that as a squared because that would be really confusing. So the notation we use quite naturally for abelian groups where we're using additive notation, the notation we use is 2a. So this is just notation, just like a squared is notation. And it's notation that matches with your common experience of doing maths. And it doesn't lead to any confusion, all being well. So in general, we talk about say NA, which means a plus a n times if n is bigger than 0. So I have mentioned this a couple of weeks ago, but I want to make sure everybody's straight on this. And if n is negative, then we just do minus a minus n times. So rather than writing a to the n, when we use multiplicative notation, we'll be writing na if we're using additive notation. Okay, so just make sure you know what notation is being used. So in general, we use multiplicative notation, but we're not going to use multiplicative notation if we've got an additive operation like this. So, having said that about notation, what does it mean for z to be cyclic? Well, I've got to find an element such that every element can be written as n times a, where a is the generator. And so all we need to do is, in fact, take a equals 1, for example. Because if I take, say, well, let's just take an integer n, then n can be written as, if n is positive, n can be written as 1 plus 1 plus 1 n times. And if n is negative, I can write it, let me just write this down. So I can certainly generate any positive integer using 1. If n equals 0, well, by definition, 0 times 1 means 0. That's just the definition. It's analogous to a to the 0 being the identity. So if n equals 0, we've certainly got 0 equals 0 times 1. And if n is negative, then well, the same thing holds. So the same thing holds. By definition, what I mean by n times 1 where n is negative, we just do minus 1 plus minus 1 plus minus 1 minus n times. So this is getting a bit squashed. That's the definition of what n times 1 means if n is negative. We just do the inverse of 1 minus n times. So every integer can be written as n times 1. When I say n times 1, I'm being a bit sloppy because that's not a binary operation, because 1 here is being regarded as an integer in the group Z, where n is also an integer, but really on the same level as this one. It's just the analog of a to the n. Okay, the n here is the integer n in the exponent. Here, because we're using additive notation, it's round at the front. Okay, so we've got that Z is generated by 1, but also just by turning around my positives and negatives, you see that Z is also generated by minus 1. Just interchange the role of positive and negative, you get Z is also generated by minus 1. In fact, 1 and minus 1 are the only generators of the integers. I'll leave you to think about that. You couldn't generate the integers by 2 using 2, for instance, because 1 couldn't be written as something times 2. In fact, in general, as I remarked in the tutorials yesterday, if an element generates a group, then its inverse also generates the group. Okay? So if you've got a generator for a cyclic group, then its inverse also generates the cyclic group. Okay? So the integers is cyclic and the integers is infinite. So this is an example of an infinite cyclic group. And in fact, it's the archetypal infinite cyclic group. We'll see shortly that every infinite cyclic group is isomorphic to the integers. So I'll just write this down now. I haven't proved it. That's an important fact. So if you've got an infinite cyclic group, then essentially, in terms of group theory, it is the integers. In particular, it's countable. So cyclic groups can't be too big. The biggest they can be is the integers. They've got to be countable. So we haven't proved that yet. I mean, if you've done the reading from Fraley, you will have seen a proof of this, but we haven't proved it in class yet. So that's the integers. Well, the integers is cyclic, but in any case, the integers is a group. What cyclic subgroups of the integers? So I'm forgetting for a minute that the integers is cyclic. I'm just thinking about the integers as a group. I can look at cyclic subgroups of Z. So for instance, let's just take the integer 5, perfectly good integer. What is the subgroup generated by 5? Well, let's use our slightly sloppy notation. It's all powers of 5. But remember, power now means I'm putting the exponent in front. So rather than 5 times 5 times 5, etc., I'm looking at 5 plus 5 plus 5. So I'm looking at multiples of 5 using that language. So it's all integers that are divisible by 5. And we use an obvious notation for that. We write that as 5z. So it's all multiples of 5. So this is the set of all multiples of 5. That's one way of saying it. Or it's the set of all integers that are divisible by 5. That's another way of saying it. I'm sure you can think of some other ways of saying it as well, depending which way you're looking at it. So the subgroup generated by 5 is just all multiples of 5, and that's the notation we use. And in fact, that's also the subgroup generated by -5. Because if you look at all multiples of 5, you're essentially looking at all multiples of -5, again by just switching the positive and negative multiples around. So whether the integer is positive or negative, we can look at the cyclic subgroup and we just get all multiples of that particular number. And we tend to use the positive number as the generator. We could equally well use -5, but we tend to use the positive number as the generator. Okay, so cyclic subgroups are just these multiples of something. So I'm switching my use of n a little bit, but hopefully that won't confuse. So the cyclic subgroups are of this form. By the way, if we take n equals 1 or -1, we just get z back. And if we took n equals 0, we'd get all multiples of 0, which isn't very big. That just consists of the integer 0, which is a trivial subgroup. So n equals 1 or n equals -1 gives z, and n equals 0 gives the trivial excuse me, subgroup. So have you got a question? So these are the cyclic subgroups of Z, and you could ask, well, are there any other subgroups of Z? And the answer is no, because as we're going to prove in a few minutes' time, and as you will have seen in your reading, if you've got a group which is cyclic, then any subgroup of that is also cyclic, and we mentioned that a few times in the tutorials yesterday. So cyclic groups are nice in the sense that if you look at subgroups of the cyclic group, you only ever find cyclic subgroups, cyclic groups as subgroups. So since these are the cyclic subgroups of Z, in fact these are the only subgroups of Z. So once we've proved the theorem that we're going to do in a few minutes' time, we now know all subgroups of the integers. So that's useful. Okay. I think I've already used the word order, but let's just write down a definition. So I'm writing this sentence down again. So let A be a group, G be a group, let A be an element of G. Then if we look at the cyclic subgroup generated by A, well, there are two possibilities in terms of its cardinality. It's either finite or it's not. So if it's finite, then the order of A, so I'm defining the word order here, for an element, notice, we've already used the word order in the context of the group. It's the cardinality of the underlying set. But here this is the order of an element. So the word order is being used to mean two different things, but happily, as we'll see, the two uses more or less coincide wherever appropriate. So if the cyclic subgroup generated by A is finite, then the order of A is just the order of the underlying group. Okay? So pointed brackets A is a group. So it's got an underlying set, the cardinality, and that's the order of A. So we could say the order of A is just the order of the cyclic subgroup generated by A. Well, if the other alternative holds, which is that the cyclic subgroup is infinite, then A is set to be of infinite order. So there's no actual numerical value associated. We just say that A is of infinite order. And just a little advert for what we're going to do later, but again it's something that you should have seen in your reading. If A is finite, then it'll turn out that the order of A is just the smallest positive power, such that if A is raised to that power, we get the identity. So it's the smallest positive power such that if I look at A to the K, so I'll say this sort again. The order of A, which is the order of this subgroup, it's the smallest k positive integer such that A to the K is the identity. And we were seeing that in the examples in the tutorial yesterday, that as soon as we got to the power that gave us the identity, the first one, then we'd written down all the elements of the group. Sorry, that's a K there. So again, that's a little advert for something we're going to do shortly. There was a tutorial question last week that showed that if you had a finite group, then for any element there had to be some power such that A to the K was the identity. And so in particular, if we looked at this finite group, there must be some power for which A to the K is the identity, some positive power, and the smallest one will turn out to be the order. As I said, we've seen that already in examples. Perhaps we should just do a quick example to illustrate that. Again, it's an example we've seen already. So for instance, we take G to be the non-zero complex numbers, and we took A to be, say, I. So this is an example we've seen before. Then we have, if we compute powers, let's just start at 0. I to the power 0 is 1. So here 1 is the multiplicative identity in C star. So 1 here is a complex number 1. I to the power 1 is I. So these first two lines are what I call the lines you get for free. The first one is a definition. Any group element to the power 0 is the identity element, and any group element to the power 1 is just the group element. And then if we start computing the non-trivial things, I squared is minus 1, I cubed is minus I. And then if I do I to the 4th, I get back to 1. And I'll put that in bracket because I've already got that. Now I've chosen to go in the positive direction there, 0, 1, 2, 3, 4. If I'd gone in the negative direction, minus 1, minus 2, minus 3, I would have also got back to 1 when I got when I got to minus 4. So although in principle there are an infinite number of powers of I, there are only 4 distinct ones. So the cyclic subgroup generated by I, although in principle it's got an infinite number of powers of I in there, there are actually only 4 distinct ones. And here we're seeing this an illustration of the fact that the order of I is equal to the number of elements in the subgroup by definition, but it's also the smallest power that gives you 1. So 4 is the number of elements in this cyclic subgroup. It's also the smallest power which gives you the identity element, and that's always true. Okay? So 4 elements in the cyclic subgroup, but 4 also appears here as the first positive power which gives you the identity element. So that's 2 numbers which are always going to be equal for finite cyclic groups. Are there any questions at that stage? Okay. Well, let's just prove this is quite an easy result. Well, I'll call it a theorem. All the cyclic groups that we've had as examples you will have observed are abelian, and that's true in general. So let G be a group. If G is cyclic, then G is abelian. So this is quite an easy proof. It'll give us a chance to remember what abelian means. So we've got 2 words here. We've got cyclic and abelian. Notice the implication is going in one direction, as I've stated it. If it's cyclic, then it's abelian. So I've got to start off with my hypothesis that the group is cyclic, and I immediately convert that into something useful. If it's cyclic, then I know it's generated by some element. So let's call that element A. So that's what I know. That's the hypothesis. And what do I have to prove? I've got to prove that G is abelian. What does abelian mean? It means that the underlying binary operation is commutative. So let's write down what we must show. We must show that for all x and y in G, that xy is the same as yx. So I'm using multiplicative notation as usual when I'm talking